Now we can introduce the concept of a subgroup. So let G be a group with operation asterisk, and let H be a subset of G. In other words, H consists of some of the elements, possibly all, possibly none, of G. Then we say that H is a subgroup of G, and write H less than or equal to G if H with the binary operation asterisk is also a group. In other words, or in particular, H has to include an identity element, so H can't be non-empty. But okay, anyway, let's look at some examples. So if we start off with the group G being the integers with addition, the identity element is 0. And let's consider the subset of the even integers. So that's a subset of all the integers. And the question is, or I guess the statement, is that it is a subgroup of Z, the integers, with addition. And by contrast, the set of odd integers is not a subgroup of Z. Why? Well, several reasons. First is the identity element is not an odd integer. That's one reason. So one reason why the odd integers are not a group, because a group has to contain an identity element. And we know that there's only one identity element for Z with addition. It's the 0. Another reason why the odd integers don't form a group is the addition is not even a binary operation on the odd integers. If you add two odd integers, you get an even integer, not an odd integer. So this set of odd integers is not closed and under the addition, and so it's not even a binary operation. Here's a theorem, the subgroup theorem, that allows us to check if a subset of a group G is a subgroup. So the conditions are that the subset H is a subgroup if and only if H is closed under the group operation asterisk. In other words, if I take two elements in H and I multiply them, if you will, that result lands inside H. A priori, or what we know so far, or at first glance, is that the group operation H1 times H2 lands in G, but we're requiring it that lands in H in order for H to be a subgroup, is one of the conditions. The second condition is that the identity element of G has to lie inside H. And then the third condition is that if A is inside H, then the inverse, previously I was denoting this A prime, but I'm going to start writing A inverse, or A to the negative 1, is an element of H. Okay, I won't prove this theorem right now anyway. Here's an example of a subgroup. So if G is a group, then the set generated by G, lowercase g, where lowercase g is a fixed element of the group G, consisting of all the powers, if you will, of G. In other words, by powers, I mean expressions G times G times G, where again the times is the binary operation associated or involved with G. It could be addition in many cases, but frequently it's multiplication, and so we just often just say times when referring to the binary operation. Anyway, so n could be a positive or negative integer. If n is negative, what this refers to is the inverse. So g to the negative 5 is g inverse multiplied with itself 5 times. So this set here, the set generated by G, in other words, all the powers of G, positive and negative, is a subgroup of G, and it's called the cyclic subgroup generated by G. Then a definition is that a group is cyclic if there exists an element of it, lowercase g, such that the entire group equals the subgroup generated by lowercase g. Let's do an example. The group of integers with addition as the operation is cyclic because it's generated by 1. It's also generated by negative 1. These two lines are not saying 1 is equal to negative 1, but it's saying that the subgroup generated by 1 is equal to the subgroup generated by -1. And why is that? Well, 1 to the n, the group operation is plus. So that means 1 plus 1 plus 1 appearing, n times, n copies of 1. And so that adds up to n. And so we'll get any integer, positive or negative, when we consider 1 to the n. Again, 1 to the -5 is -1 plus -1 plus -1, 5 times to get -5. Okay, so a non-example, which we haven't talked about yet, and I'll talk about in the next video, is the Klein 4 group. It's not cyclic because it has no element of order 4. It's a group of order 4, of size 4, with no element of order 4. I'll explain this later. I have not introduced the terminology just yet. Okay, a theorem is that every cyclic group is abelian. An abelian group is one that's commutative. In other words, A times B equals B times A for all A and B in G, the group. So the proof is that, okay, let G be a cyclic group. What that means is that there exists an element, lowercase g, of the group such that G is equal to all the powers of G. Okay, so let A and B be two arbitrary elements of the group G. We need to establish this fact, or this equation here holds. Now A then, because it's an element of the group G, it is equal to some power of G. So A is equal to G to the n, and B is equal to G to the m for some integers m and n. Then, well, A times B is equal to G to the n times G to the m. In other words, G to the m plus n. Why is this the case? Well, this is G to the n is n copies of G multiplied, if you will, together, and then you're multiplying furthermore m copies of G. So collectively, you're multiplying m plus n copies of G. And then a similar reasoning shows that that's the same as G to the m times G to the n, and that's what B times A is. So a cyclic group is abelian or commutative. Okay, now let's do some examples. So Z10 with the plus. So Z10 is the set of numbers 0, 1, 2, 3, all the way up to 9. And the group operation is addition mod 10. So in other words, 7 plus 8, you add them normally, so that's 15. But then you need to land back inside here and you do mod 10. In other words, 15 mod 10 is 5. What's the remainder? When 15 is divided by 10, the remainder is 5. And so 7 plus 8 in this plus operation is 5. Now Z10 star, those are, you start with these numbers and only take the numbers that have a GCD of 1 with 10. So in other words, you throw out the numbers like 0, 2, 4, 5, 8 that have a common factor with 10 that's bigger than 1. So in other words, 2 and 10 have a GCD of 2, so that's why 2 is thrown out. Similarly, 5 and 10 have a GCD of 5, so 5 is thrown out. 0 has a GCD of, 10 technically, and so it's thrown out. Anyway, so these are the numbers in this list that have a GCD of 1 when with 10. And so those form the underlying set of Z10 star. We'll see later why star, what the star means. It means a unit in this ring, but okay. And then we have a group operation given by multiplication mod 10. So for example, 1 times 3 is 3 in this group operation. Let's do something like 7 times 9. You do the usual multiplication. 7 times 9 is 63. And then you take mod 10. So 63 mod 10 is 3, because the remainder when dividing by 10 of 63 is 3, the last digit. Okay, so that's the group operation multiplication on Z10 star. It is a group. That's a little bit involved to check. You'd have to check that every element has an inverse. For example, the inverse of 3 is 7, because 3 times 7 is 21, and the remainder mod 10 is 1. Okay, anyway, So the point I want to make is that these groups are very different, even though the notation is very similar. They're different. Well, first of all, they have different sizes. Z10 with plus has 10 elements. Z10 star, group operation by multiplication, has 4 elements. And also to notice is that in Z10, what would previously or sometimes we write 3 squared, what that means is 3 plus 3, because the group operation is plus. And that's equal to 6. And 3 cubed likewise is 3 plus 3 plus 3. That's equal to 9. So I usually don't write 3 squared and 3 cubed when talking about Z10. I usually write 3 plus 3 or 2 times 3 or 3 times 3. But in this notation up here in a general group, when the operation is asterisk, we stick to writing things multiplicatively, even though in some specific examples it could be plus as the operation. Okay, in Z10 star, this is more familiar. That 3 squared literally means 3 times 3 because the group operation is times. And similarly, 3 cubed is 27, which in mod 10 land is 7.